Hello, everyone, and welcome to our discussion on the uniform probability distribution. In this lesson, we're going to focus on a continuous random variable in comparison to a discrete random variable, and then how this applies to probability density functions in general, and more specifically, uniform probability distributions specifically. So let's remind ourselves of what a continuous random variable is. Right? It's a variable that can take on an infinite number of values in a given range, and this usually comes from some sort of measurement. For instance, the length of each song that's in your iTunes library, or the weight or height of a bunch of people, or the volume of things like swimming pools or cans of soup. So any kind of measurement. Now, of course, we could list the values from each of the preceding examples because there would be a finite number of data values that we gathered in our sample. But we cannot list all possible values for each of those random variables, i.e. length, height, weight, volume, because each of those random variables has an infinite number of possibilities that can come from those measurements. And because we have an infinite number of values for a continuous random variable, the probability of any specific value is virtually zero. Now you'll remember that the basic idea of probability is simply good over total. And so let's just say we want to know the probability that x equals exactly 10. Well, in a continuous random variable, the good is 1, because 10 can only be done one way, but the total is infinity. So good over total is basically 1 over infinity, and that's roughly 0, right? So this means that what we call point probabilities, or probabilities of a specific point on our scale, is going to be 0. So that means when we're dealing with continuous random variables, we're going to really only look at inequalities. Right? The probability that x is less than 3, or that x is greater than 10, or that x is between 2 and 7. And you'll note that the probability that x is less than 2 is the exact same thing as the probability of x being less than or equal to 2, because the probability that x equals 2 is just 0, right? So adding that extra equal bit doesn't add anything to it, because again, those point probabilities are 0. We can't get a probability exactly at 2. We have to have some sort of interval. Well, this brings us to the idea of a probability density function, or a PDF. Not an Adobe PDF, but a probability density function, PDF. So a PDF is a function, we call it f of x, wherein we have a range. So x is going to range between a and b, and it has to have the following properties. If f of x is always greater than or equal to 0 for all the values between a and b, and the total area under the curve between a and b is exactly 1, that defines a probability density function. So again, what does it mean that f of x is greater than or equal to 0 for all the values between a and b? That just means that any value that we get out of that continuous random variable on that range from a to b, all of those probabilities have to be 0 or above, right? They have to be either 0 or a positive number, which is basically the definition of probabilities, right? And then the total area has to equal 1, because we know the sum of all probabilities has to add up to 1. So this gets us thinking that maybe the area under these curves has something to do with probability, and that's exactly what it is. So with that in mind, when we look at a uniform probability distribution, which is kind of the simplest one out there, because now we just have a random, continuous random variable where all of its values are evenly spread over the range of probabilities, i.e. we get a rectangle, right? The graph of a uniform distribution just gives us a rectangular shape. The height, the f of x, remember f of x is the output, it's the y value, it's the height of our function, is constant, it's uniform. And so since we know the total area under a probability distribution must equal 1, and we have a range from A to B, and the height is a straight line, which gives us a rectangle, what's the height of this thing? Well, hopefully you're all saying, well, it's got to be 1 over the range, right? Because length times height has to equal 1. So height has to equal 1 divided by the length, and the length is just b minus a. So there we get the height as 1 over b minus a. So f of x, the function that defines this uniform distribution, is just a straight line that is equal to 1 over b minus a, where a is less than or equal to x, less than or equal to b. So what we're saying is the b is always the bigger number, right? So a is closer to 0 and b is bigger. If we're dealing with positive numbers, which for continuous random variables, we're almost always getting positive numbers because, again, these are coming from measurements and we don't usually measure things in negative quantities. Okay, what about the mean and standard deviation of these PDFs? Well, the mean is very simple, right? If we have a rectangle, we have the area, the mean, since everything comes up equally, right? Everything has the same frequency, the same probability, then the average is simply just the midpoint. You just take a plus b and divide it by 2. You're basically taking the average of the endpoints, which is what the middle is. So the mean is just the middle of your range. And the formula for the standard deviation is also fairly simple. You got the square root of b minus a squared all over 12. But it's a little weird. It's a little difficult to understand why. I mean, why the 12, right? Well, for those of you that don't care and you just want to know what the two formulas are, there they are, and you can fast forward to the next bit. But for those of you that were curious, as I was when I learned about this, I'm going to take a few minutes and show you where this standard deviation formula comes from. Okay, so you'll recall that standard deviation is just the square root of variance. So it's much easier to do mathematics with the variance. So whenever we're trying to kind of determine a standard deviation, we go back to determining the variance, and then we just take the square root at the end, and we get our standard deviation. So we're going to talk about this in terms of variances. And you'll remember that the formula for the variance for a discrete variable, just a normal kind of set of numbers that we've been dealing with, is simply just the sum of x minus the mean squared all over n, right? So you take each data value, you subtract the mean from it, you square those numbers, you sum them all up, and then you divide by n, and then that's the variance. You would take the square root, that gets you the standard deviation. Well, instead of dividing by n, we can think of this as just multiplying by 1 over n, right? That's the same thing as dividing by n. And now we can really think about that as just multiplying by f of x, where f of x is a function that represents the probability of each of our x's. Because when we're talking about a finite set of numbers, right, a discrete counting of numbers, n is simply our sample size. So 1 over n is simply the probability of each individual number in our set, right, because it shows up once out of n. So 1 over n ends up being that probability. Now, to use this formula, this whole sum times the probability thing, for a continuous variable, we need to make one minor change. And that's because we can't add up an infinite number of things. So that finite summation sigma symbol has to become an infinite sum, which is the integral from a to b. Now, integrals are done in calculus, so if you've never done calculus and you don't know what an integral is, that's okay. You don't really need it to understand where we're going to go with this formula. Just know that the general formula for the variance of a continuous variable is now going to be the integral from a to b of x minus the mean squared times f of x dx. Again, where f of x is the formula for the curve that is created by the PDF, right? Because the curve designates the probability of each thing. If you have a bell curve, the stuff in the middle has a higher probability because it's got a higher peak to the curve. The things show up more often, and out in the tails, it's lower. because they're less likely to occur, right? So that f of x is just the formula for the curve that creates our probability distribution function. And we'll remind ourselves that when we're dealing with a a uniform probability distribution, our f of x, our curve, is just a straight line that is described as 1 over b minus a. And we also know what the mean is, right? We calculated that before as a plus b over 2. So with those two pieces, we can sub those into our general formula, and now we get the integral from a to b of x minus a plus b over 2. That's just our mean, still squared. And instead of f of x, we're going to put in the specific one of 1 over b minus a dx. So there we have it. That is the beginning of trying to get to this whole divide by 12 weird stuff. And the following is just going to be a whole bunch of algebra. So let's see where we go next. All right, so let's start by going ahead and squaring this, right? Writing it all out. And I'm going to ignore the other pieces because we're just going to work on this, right? So x minus a plus b over 2 times x minus a plus b over 2, right? And then you FOIL it out, or like I like to teach, you just take the first one, multiply it through, take the second one, multiply it through. So you get x times everything, right? Gives you x squared minus x times this whole a plus b over 2, right? Then you take this through, so you get minus another x times a plus b over 2. And then finally, this one times this one gives us plus a plus b over 2 squared. We can combine these two terms, and we get x squared minus 2x times a plus b all over 2, right? That's what happens when you put a fraction with a whole number multiplied together. And then a plus b over 2 quantity squared. These 2's cancel. And we finally, kind of bring it all out to clean it all up as just x squared minus x a plus b plus a plus b over 2 quantity squared. Now we have to deal with the integration, right? So we've got all of this times 1 over b minus a, and then dx. Well, you probably don't know, but I'll just, I'm not going to describe how integrals work, but if you have a constant inside an integral, you can just take that and put it out front. So it just becomes the 1 over b minus a as a constant times the integral, right, from a to b of all this stuff, x squared minus x a plus b plus a plus b over 2 quantity squared, and then that whole thing dx. Okay, now we're going to take the integral, and I'm just going to do it. It's not explain how integrals work, but basically powers go up by 1, and then you divide by some stuff, and just trust me that this is the next step, and then the rest will just be algebra. So if you know how to take an integral, you'll know how we get to this next step. But otherwise, you'll have to take a little calculus to get there. Okay, so this is what we get when we take the integral. Here's that constant that was out in front. Here's that expression that we've basically anti-differentiated, and then we're supposed to evaluate it from a to b, which just means first you plug in b, then you plug in a, and you take the difference of those two. So we're just going to get 1 over b minus a times this thing evaluated at b minus the other thing evaluated at a. So that just means we're going to have b cubed over 3 minus b squared over 2 a plus b plus this right here, b times a plus b over 2 quantity squared. So there's that piece, and then we have to subtract the same thing, and this whole thing is being multiplied by that constant. Then we have to do it at a. So a cubed over 3 minus a squared over 2, a plus b, plus a times a plus b over 2 quantity squared. Right? So it's nothing difficult. It just gets messy with all of this stuff. Now, again, feel free to fast forward at any time and not follow along with all this because it's just some messy algebra. All right, let's clean it up by basically kind of bringing like terms together, right? So we're going to bring the cubes together, the squareds together, and so on and so forth. So we got b cubed over 3 minus a cubed over 3, right? This piece and this piece. And then we have minus b squared times a plus b all over 2 plus a squared times a plus b all over 2. Why is this a plus? Because we're subtracting and subtracting, right? We're minusing a minus. Then we have plus b minus a all times the a plus b over 2 quantity squared, right? Because here's b times it, and then minus, I shouldn't do that, makes it look like an equals, minus a times it. So again, we're just kind of combining like terms, cleaning it up a little bit. Now, we've got, some fractions in here. We could also combine this piece and just make it b squared and a squared together. And then we've got a fraction of 3, a fraction of 2, a fraction of nothing. So we can put a common denominator of 6 or anything else. We end up doing 12 because it's going to give us the numbers that we need to get a perfect cube. That's where we're going with all of this. So basically we're going to change everything to be over 12. So this doesn't change, right? It's still on the outside. And now this over 12 is just going to become 4b cubed minus 4a cubed all over 12. And then this piece, right, becomes plus a squared minus b squared. We just put them together, and instead of making a minus, we just put this piece second, right, times a plus b all over 12, but this started at 2, right? So we need a 6 out in front of here. And then plus, again, we need to get this over 12, but we already have this 2, and if we square it, right, if we square it, we just get a plus b quantity squared all over 4. So we really just need a 3 to bring it up. So we're just going to have a 3 times b minus a times a plus b quantity squared, and that's all over 12. I should have written this a little further over here so it wasn't in our way. But you get the idea. Okay? So there's that. Again, all we did is put everything over 12 so we can then kind of bring it all together and make it one big happy fraction. Now I'm going to skip some steps, let you guys do some of this algebra yourself. But basically, if you distribute the 6, right, and the a squared minus b squared, basically if you multiply all this together, put it all over 12, and add all the bits and pieces together, it's going to reduce down quite nicely to this. And like I said, you can do it yourself and double check your work. You're going to get b cubed minus a cubed plus 3a squared b minus 3b squared a all over 12. And then this, if you don't recognize it, is a perfect cube. This becomes 1 over b b minus a times b minus a cubed all over 12. And of course, the b minus a and the b minus a cancels. And that's how we finally just get to b minus a quantity squared all over 12. Ta-da! So that's the variance. And then, of course, the standard deviation is going to be the square root of that. B minus a quantity squared all over 12. All right, so that's the long-winded explanation of how we got there. Okay, now that we got why it's divided by 12 out of the way, let's look at some examples. So let's just say that the amount of gasoline that is sold each day at a service station is uniformly distributed with a minimum of 2,000 gallons and a maximum of 5,000 gallons. And we want to find the probability that the daily sales will fall somewhere between 2,500 and 3,000 gallons. Now, I suggest that while you're learning this and you're doing these types of questions, if you aren't given a picture, please always draw a picture. It's very simple. It's just a silly little rectangle that you label, right? You give the lower end, the upper end. You give yourself a couple little vertical lines to kind of show what you're looking for. Label those. And it just, we're visual creatures. It helps us to understand what the heck is going on. Okay, the first thing we always have to figure out is what's the height of our probability distribution function. And with the uniform, right, remember it's always just b minus a. So in this case, we have 1 over 5,000 minus 2,000. So we're going to get our height is just 1 over 3,000. Our range of what we're looking for is from 2,500 to 3,000. So very simply, we get that distance, right? That the width of that blue bar is just the upper one minus the lower one. So there's the 3,000 minus the 2,500. We've got the height of 1 over 3,000. We do that math and we get 0.1667. So again, all we're doing is finding the area of that rectangle, which is simply base times height. Length times height, width times height, whatever you want to call it, right? It's basically the distance in the x direction times the distance in the y direction. And so here's our distance in our x direction, and here's the distance in our y direction, base times height. And we get this, which we can change and say that there's about a 16.67% percent chance, if we round to 2 decimals, that our fuel sales on any given day are going to fall between 2,500 and 3,000 gallons. So what if we want to figure out the probability that the station sells at least 4,000? Well, again, draw a picture. Here's 4,000 or above. And we've got our height of 1 over 3,000. If it's 4,000 and above, we've got a width of 1,000, right? 5,000 minus 4,000. We do that math, and we get 0.3333, and we go, it's basically 33 1/3% that that's going to happen. Okay? Nice and simple. Don't make it harder than it is. We're just finding areas under rectangles. All right, let's look at another example of people arriving at a bus stop at random times, and then the time that they wait for the bus to show up is going to be uniformly distributed from 0 to 30 minutes. And we want to figure out the average wait time for the bus. Well, remember the formula for average is simply just kind of the average of the endpoints, right? It's the midpoint kind of idea. So you just do a plus b, divide by 2. So in this case, 0 plus 30, divide by 2, 15. So our average wait time is going to be 15 minutes. Then, what's the standard deviation? Well, we use this funky little formula that we derived earlier in the video. If you sat through that boring spiel, and we put in 30 for B, 0 for A, we get 30, we square it, we divide by 12, we take the square root, and we get 8.66. So the standard deviation is basically 8.66 minutes. Now, what's the probability that a passenger will wait more than 25 minutes? Well, again, we've got a nice little rectangle. All we're doing is finding the area of this rectangle. We know the height of it because the base is from 0 to 30, so the height is going to be 1 over 30. So there's our height of 1 over 30. And then if we're going from more than 25 minutes, we go from 25 up to the maximum of 30, and that is a width of 5. So there's our base of 5, right? Height times base. And we get 16.67 again. That's a coincidence that we got that from the previous example. So then we could ask the probability that a passenger will wait between 10 and 20. Again, draw yourself a nice little simple picture. From 10 to 20 is a base of 10. We still have a height of 30. And again, we get that 33.33%. Again, just pure coincidence that we keep getting these same numbers. It's just the way we set up these examples. All right, let's look at a slightly more complex example. And it's only slightly more complex because we're not going to start at 0 and end at something. We're going to start at 1.9 and end at 3.8, similar to the gasoline question. But the gasoline question only asks for some basic easy things like finding probabilities. We're now going to take it up a notch and find some x values that correspond to probabilities and so on and so forth. So first, let's start off with the general stuff. We want to know the mean, we want to know the standard deviation. Then we're going to do some of the basic probabilities, and then we're going to figure out a percentile. Okay, so the first one, what's the mean of this distribution? Well, remember the mean is that simple formula of A plus B over 2. So in this case, it's 1.9 plus 3.8 all over 2, which of course is, what is that, 5.7 all over 2, which gives us an average of 2.85. All right, how about the standard deviation? Well, again, we've got a fairly simple formula. Of B minus A squared all over 12. All right, plug in what we got. So 3.8 minus 1.9 squared all over 12. Of course, 3.8 minus 1.9 is 1.9 squared all over 12. And then stick that in your calculator, and you get 0.5485 if you round to 4 decimal places. Okay, how about the next one? Probability that they weigh exactly 2.2 kilograms. Well, what do we know about the probability of precise exact numbers when we're on a on a continuous random variable? We know this answer is just 0. All right, what next? Probability to weigh between 2.3 and 2.8. So here is my rectangle. Looks like my rectangle is leaning. 1.9, 3.8, and we want something between 2.3 and 2.8. It does not have to be to scale. It does not have to be perfect. You're just giving yourself a little picture so you can kind of figure out what you're doing. And you go, oh, area of a rectangle. I know what the height is, right? Because I've got my total distance here. My base, my total base, we figured out was 1.9. So this height has to be 1 over 1.9. And the area that I'm looking for here, this base, is just 2.8 minus 2.3, right? The difference of those, which is 0.5. So the probability is just going to be my 1 over 1.9 times 0.5, which just gives us 0.5 over 1.9. Of course, you throw that into your calculator, and you're going to get an answer of 0.2632 if you round to 4 decimals. All right, how about more than 2.28? Well, more than 2.28, here's 2.28. And my end, remember, is 3.8. So now I know that this base is 3.8 minus 2.28. And that is 1.52. So there's my base. I'm going to multiply it by the whole 1 over 1.9 thing again. And that gives us basically 0.8. Fantastic. Okay. So far, so good. Pretty easy, right? Just drawing our pictures. Here's where it gets tricky. Now we've got a given condition. What's the probability that the fawn is going to weigh over 2.3 given that it weighs less than 3.6? Okay, well, remember our original was 3.8 and 1.9. So let's say that here is 3.6. And then we want to know that it's over 2.3. Well, a given probability, all it does is it changes your total. Instead of our total range of possible values for our continuous random variable being from 1.9 to 3.8, we're now told that it's less than 3.6. So now our possible range is only from 1.9 to 3.6, and we get a whole new answer. Instead of 1.9, right, we do 3.6 minus the 1.9, and we get a range of 1.7. So this given condition has basically just shrunken our total range from 1.9 down to a range of 1.7. Now the height doesn't change, right? I mean, this is still the same bar. So this height is still 1 over 1.9. But we're now looking for the probability that something weighs over 2.3 given that we're in this range. So if it's over 2.3, that means we're looking for this area, which is easy to find, right? That's got a base of 3.6 minus 2.3, or 1.3. So the area of this is going to be 1.3 over 1.9. 1.3 over 1.9. And if we do that in our calculators, we're going to get a nice fun decimal of 0.6842, let's say. 0.6842 if we round. So that is the good area that we're looking for, right? But that's not our answer, because we want to know the probability that this happened given that we were only within this area. So this yellow is good, but this entire block from here down to here is our new total, and that is 1.7 over 1.9, right? Which gives us basically 0.8947. And now, if we do good over total, basically this one divided by that one, we're going to get the ultimate answer of 0.7647. That's the actual probability given, right? So the probability that it's over 2.3, given that the whole thing is less than 3.6, it just means that we're looking at a smaller total, and then we're figuring out the good area inside that smaller total area. Now, some of you may have recognized kind of a shortcut, and that is the fact that since we have a uniform height, instead of looking at the ratio of area over area, we could really just look at the ratio of base over base, because they have a constant height. So we could have gotten the same answer had we just done 1.3, because that's the base of the good stuff, divided by 1.7. And that also would give you the exact same answer. Okay, on to the last one. We want to figure out a weight that represents being in the 46th percentile, starting at 1.9, ending at 3.8. Boy, that's a terrible line, but you guys know what's going on. Okay. Well, the 46th percentile just means that we're going to have a cutoff, right? We're going to have some x value, and over here is going to be 46% of our data. Well, obviously my line's in the wrong place because it should be less than half, But again, we don't care about the picture being accurate to scale. If this is 46% of my area, doesn't that mean that this has to be 46% of the total length, the total base? We know the total base is 1.9, right? If we go from 1.9 up to 3.8, that's a distance of 1.9. So all we have to do is multiply that by 0.46 to find how big the base of our new rectangle is going to be. And that is a distance of 0.874. So we know this distance from here to here is going to be 0.874. Now that's not a probability, that's a distance, and the reason why it's a decimal distance is because we're just dealing with really small numbers. So the answer, this x, is just the value that is this far above the starting point. So we just take that and we add it to 1.9. Because remember, the 0.874 wasn't x, it was the distance. It was the length of the base of the rectangle that we needed to give us this area that represented 46%. So we found that this distance, this base here, was a distance of 0.874. And if we add that distance to 1.9, we get the actual x value of 2.774. So if a newborn fawn comes out weighing 2.774 kilograms, that fawn would be in the 46th percentile of newborn fawn weights. All right, that's all I got for you for uniform probability distributions. I hope this helped.